Now, if anyone's been to any of my talks before, you're probably prepared for what's about to happen. But I like a bit of self-care, and especially as we've just taken a bit of time for lunch, I think it's important we take a moment for some self-care. So if you are willing and able, please stand up. Make sure you've got a little bit of space between you and the person next to you. And I want you to give me a big thumbs up. Both arms out as far as you can go. Big thumbs up, yeah? And then when you take your arms, I want you to stretch them back as far as you can go. Feel that in your back. Can you feel that in your shoulders? Don't stick your chest out, just feel that in your shoulders, yeah? Now breathe in and out. Breathe in. Feel that stretch, yeah? And out. And then one last time, breathe in. And out. Right, give yourself a round of applause. Do you feel better for that? That's a really good stretch to do. We're all hunched over computers. We're all sitting on these chairs uncomfortably. That's a great way to loosen up those muscles in your shoulder. Highly recommend. Now, we're actually going to be talking a little bit about self-care today in some ways. We're going to be looking at how we can use an IoT device to prove that the best thing we can do in meetings is leave. None of us like meetings, and it turns out we make dumb decisions in meetings, and the best thing we can do is go for a walk. So hands up if you've ever fallen asleep or almost fallen asleep in a meeting. Who's actually fallen asleep? Come on, confession time. A few people have actually fallen asleep. Okay. And who's ever fallen asleep during training or a conference talk? Actually fallen asleep? Right. If anyone starts snoring in this session, just nudge them. Okay. Now, I've not actually completely fallen asleep, but I have got close. And the first time I ever really noticed this, I was working for an investment bank in London, and they sent me on a SQL Server training course. And we're in these tiny little rooms, you know, probably 4 chairs in 2 columns, 5 or 6 rows. We're delving into SQL Server. And kind of by the late part of the afternoon, my eyes were just, you know how you do that kind of, just, kind of phase out. And it just happened a lot. And I've noticed that again. I will go to meetings, and I will start to just drift off a little bit. And in general, the main thing I found, the correlation between these different occasions where I would start to drift off, is small rooms. Lots of people in small rooms. And that's kind of interesting. Okay, why does that happen? And it turns out, actually, it is a thing. And the best thing you can do to get over this, the best thing you can do to stop yourself falling asleep, is to go for a walk, or at the very least, go outside. You feel this. Those meetings you've been in, drifting off. Meeting's over, you get up, you walk out, and suddenly you feel refreshed. Yeah? You notice this fact? You're not so tired. Just by leaving the room you are in, you are not as tired. And the reason we are sleepy is this little guy. Carbon dioxide. 1 carbon molecule, 2 oxygen molecules. Nice straight line molecule. You've got double bonds between the carbon and oxygen for those who are chemistry geeks. And it's small, not particularly scary looking thing, but this is the reason you fall asleep. Now CO2, it's produced by animals breathing. We are all creating CO2 right now. We're all CO2 generators. We breathe in oxygen. That is combined with carbohydrates. We burn this. We create water and carbon dioxide. Who did that at school? Who learned all this stuff at school, yeah? Yeah, you all did. We create carbon dioxide as we breathe out. We're also on this planet, we're creating carbon dioxide through burning fossil fuels. We need to think about being green. Keep talking about being green. Got to be green. Green is good. Burning fossil fuels creates carbon dioxide. Now, carbon dioxide does have a use. It is the food of plants. Again, elementary school science, photosynthesis. We have carbon dioxide and water plus sunlight gives us carbohydrates. That's what happens in plants. Humans consume the plants. We convert that carbohydrates with oxygen into carbon dioxide and water. And thus, the cycle continues. So it's very, very important. But this is the thing that kills meetings, where we fall asleep, kills classrooms, where our kids fall asleep, and kills the planet. Now, those of you who put your hand up say, yeah, I've drifted off in meetings. Think about all your children. I mean, who here either has children or was once a child? Yes. All of you. So you've all been in these situations where you've been in a meeting, essentially. You're in a classroom with other carbon dioxide generating life forms in these rooms, and carbon dioxide is going to make those people in those small rooms drift off and fall asleep. Now, I'm going to do a quick demo to show you the carbon dioxide levels in this room right now. So I'm going to zip over here, and I've got the carbon dioxide sensor, which we'll dig into in a minute, but we are currently kicking out 454 parts per million of carbon dioxide. And that's actually really, really good. I was hoping that number would be higher. But that's good, so hopefully no one's going to fall asleep. And then just to prove that we breathe out carbon dioxide, I'm just going to blow on my little device down here. It's not supposed to go to 0. I'm dead. Okay. There we go. Now it's starting to go up. I think in that case, where my breath blew across it, it just knocked all the molecules away. But we're going up. We're hitting 1353, 1763. So that is picking up the carbon dioxide that comes out of my lungs. So we can see that just by breathing in close proximity to this device here, carbon dioxide levels have gone up. So carbon dioxide levels have a close correlation with health. A good level, green is good, between 400 and 800 parts per million. This is how we measure carbon dioxide. In fact, if I just zip back to what I had now, but you see it's ppms, parts per million. That's how we measure things like gases in the atmosphere. Between 400 and 800 parts per million, that is good. This means for every 1 million gas molecules in the air, and again, you probably remember from basic science, nitrogen is the main component of air at like 70-something%, then oxygen, 20-21%, argon, carbon dioxide, and other things. And so out of 1 million air molecules, most of them nitrogen, some oxygen, if between 400 to 800 of those are carbon dioxide, that's generally okay. In fact, the average out there, outside, is about 400 parts per million. You've probably seen this number when we talk about climate change. Yeah, we've been trying to keep that number below 400, but really it's kind of creeping up. 400 is kind of that danger level for the planet, but kind of okay for us as humans. When we kind of hit the 800, that's really the upper limit. We don't want carbon dioxide levels really above that when we're inside. When we hit 1200, this is poor levels. This is drowsiness and poor air. And if you have a weak constitution or weak blood supply, or low blood pressure, you can actually faint at these kind of levels. And then when we hit 1800, this is dangerous. Poor concentration, increased heart rate, headaches, and sleepiness. Now, these numbers do actually correlate to people doing dumb things in the workplace. So research from Harvard University found that cognitive scores decreased by 21% when the levels of CO2 jumped from 550 parts per million to 945 parts per million. This means you have a slower response time and you are less accurate at making decisions. Now, who's been in a long, boring meeting where people have made some really stupid decisions and you come out of it and go, why the hell did we agree to that? We've all seen this, yeah? This is because the carbon dioxide levels are high and your ability to reason and think decreases. So ideally, you want to have short meetings and you want to go outside because that makes you smarter. Now imagine the impact this is going to have on our kids. We put kids in classrooms and the CO2 level goes up and their decision-making skills drop and they have to learn in these environments. Not ideal, not good at all. Now CO2 levels also have a correlation with disease. Who knows what that is? Okay, that's coronavirus. That is COVID. Yes. Now, it turns out, in a paper that was published in Nature back in April last year, that high levels of carbon dioxide increase the aerostability of the COVID virus. So if one of you has got COVID right now, you're breathing out that virus. As it goes through the atmosphere, it will eventually break down. More CO2, the less chance of it breaking down. But also, as well, high CO2 levels have a correlation with high incidences of respiratory illnesses. Not a causation, a correlation, simply because it measures ventilation. So the more ventilation we have in a room, the closer we get the CO2 levels to the average level outside. 400 is the average level outside. As we saw from my little device, we were ticking around at, it's dropped back down since I've been breathing, but we're about sort of 550s now. It was 400 earlier. We now have more people in the room. But the better the ventilation, the lower that number will be, because you're taking air out, bringing fresh air in. And the same thing happens with respiratory illnesses. So if I've got someone with a cold and they're coughing and sneezing the cold virus, the better the ventilation, the less of that virus is going to hit everyone else in the room. And so just by saying, yep, our CO2 levels are good, we're probably going to be in a better place for avoiding disease. And actually, it's kind of one of the failings we had as humanity with the recent COVID virus is we know all this kind of stuff, and we didn't do much about it. In classrooms, it was, let's open the windows, let's open the doors, let's get airflow going through, instead of going, let's improve the ventilation. So it is happening, but this was our chance a couple of years ago to really improve ventilation to reduce the risk of disease. We didn't do it, and in our classrooms, we still have colds going around. I have a 12-year-old, my wife is an elementary school teacher, I am perpetually sick because one person comes into the classroom with germs, no ventilation, germs get spread. My wife picks it up, my kid picks it up, I get sick. Not a fan of that. So yeah, the easiest way to get away with these high CO2 concentrations is to go outside. So if we start getting drowsy, what we'll do, we'll all just get up, we'll go outside and we'll carry this on in the park, yeah? Yeah, cool. So what do I actually have here? I've shown you me breathing at something. I have a device here. What have I actually got? So this is my little device. It is a Raspberry Pi. I'll dig into what that is in a minute. Some lights, a little thing on a cable, and a little magic box on some cables. This is what we call an IoT device, an Internet of Things device. Who's done IoT before? Obviously, Cliff, I know you have. A few folks. Cool. Great to see this. So the Internet of Things, the concept of this is we have these devices that have some form of interaction with the real world, and then we connect these devices either together in a kind of an isolated system or to the internet. So we are building this, unlike the kind of internet of computers, we're building an internet of these different connected devices. Sometimes these just connect themselves and share information. Sometimes they connect up to the cloud. Now, these Internet of Things devices are based around what we call sensors and actuators. A sensor is a device that senses the real world. It picks up physical properties of the real world. A carbon dioxide sensor, a temperature sensor, for example, humidity sensor, pressure sensor, pollution sensor, vibration sensor. These are all devices that turn physical attributes of the world into electrical signals that can be processed by a computer. On the other end, we have actuators that turn electrical signals into physical interactions with the real world. So like one of the canonical examples of this is an automated watering system. So if you have a garden, you probably want your garden to be nice and watered so that your grass doesn't die, your flowers don't die. And rather than just watering it every night, you can take a soil moisture sensor, stick that in the ground. That measures how wet the soil is. If the soil is not as wet as you would like, you can then use an actuator to turn on the water and you water your garden. It's actually used massively in digital agriculture. So a lot of these big farms, they use moisture sensors to work out, do I need to water my crops or where I need to water it? Yeah. Big farm, sensor here, sensor here, sensor here, sensor here, measure that, turn on watering where we need it. Now, you can even go kind of further with these IoT systems. Is as well as just using the information you gather from a sensor to control an actuator, you can also use this to make smart decisions. You can run analytics in the cloud, for example, to help you decide what to do. So thinking about this automated watering system, my field is dry, I need to water it, but my analytics service in the cloud says, oh, hang on a minute, it's going to rain tonight. So rather than you water it yourself, let's wait for the rain to happen, see what happens to soil moisture, and then water it if we need to. So it's kind of this idea of I'm not just gathering data and impacting on the world, I'm using that data to make smart decisions. Yeah, and there's kind of a big rise in things like AI for doing this, but this is the cool AI, not this modern generative rubbish. It's kind of actual AI that looks for patterns in data. There's a lot of really cool stuff happening in the IoT space. And this, yeah, I mentioned it for soil moisture measurement, but it's kind of everywhere. We have it in trucking fleets. I have a whole lot of trucks. They have frozen food in them. I have temperature sensors inside the truck. Oh no, my temperature's too high, I cannot deliver this food. Or you bring smarts, oh no, my freezer's starting to fail, I'm not going to drive this to the Sainsbury's that's 20 miles away because my food will be too warm at that point. Instead, I'm going to reroute my truck to Sainsbury's that's 5 miles away because my food won't be too warm. So lots of kind of smart, cool things you can do. Now, actually looking at what I've got here, the base board I've got here, this is a Raspberry Pi, one of the finest things to come out of Great Britain in recent times. Who's used Raspberry Pis? Yes, we all love Raspberry Pis. It's a Raspberry Pi 5 because I like to go overkill for these kind of things. Fully featured Linux computer, 2.4 gigahertz quad-core ARM processor, 8 gigs of RAM. They've just released a 16 gig version. I want one. And it's very, very cool. And it's got a little active cooler, which you can't really see very well, but it's like a little fan, an active cooler in there. And then I put a 256 gig SSD in there because I can. It's got a PCIe slot, so rather than rely on an old SD card, I've got 256 gig SSD. And that's kind of the thing, the core engine that drives everything. Now, these Raspberry Pis, they are full-featured Linux computers, and obviously, with Linux, we can use the programming language of our choice. So rather than with the teeny tiny microcontrollers that you can get for a few bucks, where it's like, you have to use C, I can use whatever language I want on here. So I can use Java, Python. In my case, I'm using .NET. Now, what's cool about these Raspberry Pis is the GPIO pins. These little things here, general purpose input-output pins. They are great. These pins allow you to send electrical signals to hardware or receive electrical signals from hardware. I can plug anything into those because they're general purpose pins. Some pins provide power, some pins are ground to make a circuit, some pins are there for you to send signals to hardware or receive signals from hardware. And it's great. There's so many things you can get that plug into those pins. And so I can plug in all manner of different sensors of my choice. These are originally designed to be a hobbyist board. You know, kids want to learn how to code. We give them a Raspberry Pi for 30 quid. They plug it into their TV. They plug in a keyboard. And hey presto, you've got a paparazzi. Hey presto, you have got a really cool home computer for kids to learn how to code. And obviously, they've gone from strength to strength to strength. Now, very, very popular in the IoT space because they are very, very powerful boards that you can do a lot with. So not just these boards you can buy, the general purpose ones for the home user, you could even get compute boards that are designed to go into electronics that you run in a factory, in automation systems. You know, they have this Raspberry Pi compute module that's designed for industrial use. Fantastic devices, love them to bits. Now, the sensor I've got in there is a Grove SCD41 CO2 sensor. So inside this box here, is a SCD41 CO2 sensor, which is a NDIR. It's a photoacoustic NDIR sensor. That's an infrared sensor, and what it does is it shines infrared light at the CO2. The CO2 vibrates, and then gives off a photoacoustic wave, which is picked up by a microphone. Now that sounds a bit complex, but essentially you are shining a laser beam to make carbon dioxide scream, and the louder it screams, the more carbon dioxide you've got. So imagine if I shone a laser beam at, say, you two over there, you would scream at a certain volume, but if I did it to the 4 people in the row behind you, they would scream louder, so I could work out how many people I've got from your screams. I do not condone firing lasers at people to make them scream, but CO2 is evil, therefore I don't mind firing lasers at it. But that's how it measures that. And then based off, say, the volume, we get an idea of the concentration of CO2. Now, these sensors do have to be calibrated every now and again. So you just take them outside, it assumes outside is 400 parts per million, and then it uses that to kind of work out, going forward, what the level should be. And this is connected using a thing called a Grove connector. So Grove comes from a company in China called Seed Studios with 3 E's. Love this company to bits, absolutely fantastic. And they make IoT hardware that's easy to use. When I say easy, what I mean is I have this lovely connector board that sits on top here, and I just get a cable, and I just plug it in. I'm not putting individual wires in. Who's ever done things with breadboards and soldering and unleashed the magic smoke accidentally? Yeah, you don't get any of that. No magic smoke here because you've got these well-designed sensors. They do a whole lot of different things, Seed Studios. They do microcontrollers all the way up to really powerful GPU boards. This whole kind of Grove thing. And they're actually doing a lot of work in the developing world to try and bring IoT to the people who really could benefit from it but can't afford to buy it. So one thing they're doing is they're working with small villages in Southeast Asia where they will stick soil moisture sensors in people's farms that connect over radio waves. And then when there's one person in the village who has enough privilege to have an internet connection, that one person's computer gathers all the data from all these farms and helps them make decisions about smart watering to reduce the watering impact. And then they're adding things like pollution sensors to try and help them be more environmentally friendly. So fantastic stuff Seed Studios are doing. Not affiliated with them in any way, shape, or form. I just love their products. Amazing people. Now, just to geek out a bit, this SCD41 uses a thing called I2C. That's inter-integrated circuit. Okay, an I2C is one of the types of buses that you can get to connect hardware together. So when you think about like your PC or your laptop, you have like USB sockets, HDMI sockets, and they all send data in different ways. The same happens with IoT devices. There are different ways in which you can send data to an IoT device. And this uses a thing called I2C. It connects to 4 pins. 2 of the pins provide power, VCC and ground. That gives it power. And then it's got a clock pin that kind of ticks so you know what speed you're sending data, and then a data pin. Now, every single I2C device has an ID, and that's usually hard-coded on the device. So every single SCD41 you buy has the same hard-coded ID. And the way I2C basically works is something says, hello, I'm ID47, I want to send some data. And then everyone stops, it sends data, and then says, hello, I finished sending data now, and then it stops. And so every device can take turns sending data. Not the fastest, but it's still fast enough for a lot of the information that you are gathering. And so even the actual Raspberry Pi itself could be an I2C controller. And then on these Grove boards, this is one of the things I love about Grove, is you have all the different ports, analog, digital, UART, I2C, and they're just labeled. And so I know, I buy this, and the instructions say, plug it into the port labeled I2C. Plug, done. Not worrying about cables, not worrying about breadboards, no magic smoke. So let's actually get a stream of data coming in, and you'll see, let me just stop this and then restart it for reasons. This is the same stream of data coming in that we just saw. Give this a second for it to connect. Oh, we're. So it took a few seconds, then another measurement after a few seconds, and then a few seconds more, get another measurement. And that's kind of how this device works. It takes a bit of time to fire the laser beam at CO2 to make it scream. And so this device is designed every 5 seconds, it gives you a reading. Fire the laser, listen for the screams, send the data. Fire the laser, listen for the screams, send the data. And actually interesting, you'll notice it was 598 just now, and it's dropped. Why do you think it's dropped? I walked away, exactly that. Just by being here increases the CO2 concentration because I'm talking. Do you remember during COVID times we said, oh, don't talk so loudly because you can spread more virus? Same kind of idea. I'm talking, I'm generating CO2, and probably in a minute we'll see that go back up just because I'm kind of standing here and doing things. But yeah, every 5 seconds the data comes through. Now, I built everything for this using .NET. Who's a .NET dev? Ah, I like this. We're all .NET devs. Cool. So there is a .NET IoT library out there. And that allows you to run IoT applications on any device that supports various different IoT hardware. Now, as mentioned, Raspberry Pi, we know this. It's a Linux computer. .NET runs on Linux. I have got .NET 9 stored on Linux, and it's got access to things like those GPIO pins. There are libraries that interact with the GPIO pins. And inside the .NET IoT NuGet package is a whole load of what they call device bindings. And this is specialist code to talk to a whole range of these different IoT devices. So when you go and buy a hardware from Seed Studios or wherever, there's probably already code to interact with that hardware. You don't have to write it yourself. It's not like, oh, this is I2C, so I have to write low-level code to talk to I2C and then interpret the binary data that comes back. No. There's just these nice device bindings. Means you can write a very small amount of code that interacts with your hardware. So for example, this is the really 4 lines of code that you need to interact with an SCD41 sensor. It's great. We start off with connection settings. Do you remember I said all I2C devices have the same ID? That's the default I2C address for my SCD41. So if you buy any SCD41, that should match the address. Geeky note, you can hack the address by soldering, moving jumper pins, things like that. But essentially, if you just get one out of the packet, that's the address. So we set up our I2C connection settings, create an I2C device, and then set up our sensor, connect to that I2C device. And you can have multiple I2C buses on your hardware, so you can kind of configure which bus it's connected to, stuff like that. But essentially, this gives us our sensor. Then we have an asynchronous method. It says read periodic measurement async. Do you remember I said it takes 5 seconds to get data? So this method, you call it, you wait 5 seconds, and it returns a result. Hence why it's async. Now what comes back is 3 values. This sensor does carbon dioxide measurement, and it does temperature and humidity as well. But you'll notice we have a type of volume concentration. And this, to me, is one of the really cool things about the .NET IoT library, is it uses a library called UnitsNet to provide strongly typed units. So I can imagine you have a temperature sensor. The temperature that comes back is 12. 12 watts. Is that 12 Celsius? I live in the US, where we are very, very backwards, and we use Fahrenheit. Some nonsense. So if it comes back as 12, is that 12 Fahrenheit? Is that 12 Celsius? Is that 12 Kelvin? We don't know. Same with this. If this CO2 came back as 400, is that 400 parts per million? Is that, what does that mean? And by having these strongly typed values, we can tell what it means. So volume concentration comes back, and I've got various different methods on the volume concentration to get that in different formats. So I can say the value of my volume concentration in parts per million, please, and that will spit back the 400 parts per million, 500 parts per million. So that's very, very powerful. And that's literally the code that I've got inside my device. Here it is here. Very cool. Now, this is all the thing side of it. So on the thing side, we have hardware, Raspberry Pi, SCD41 sensor, done with the seed growth system, and we have software, we have .NET IoT. But I want to make this an Internet of Things device. So let's talk about the Internet part of this. The I in IoT stands for Internet. These devices are more powerful if I can connect to the cloud and I can do stuff with the data. And the standard way to connect an IoT device to something else is using Message Queuing Telemetry Transport, or MQTT. Who's heard of MQTT? Okay, few hands. Pretty cool. So MQTT, originally designed in 1999 by Andy Stanford Clark from IBM, another great British invention, and it was used originally to send data about oil pipelines. So when you have oil pipelines set up, you send data around. Now MQTT, it's a pub-sub system. So you have an MQTT broker, and then things can publish to that and subscribe to that. And you publish to named topics, which you can divide up with slashes. So you can publish to /environment/CO2, whatever you want. And you can subscribe to either named topics or wildcard topics. So I can publish to /environment/CO2, and then I can listen to either /environment/CO2 or /environment/star, and that way I get anything that's sent to any topic. So kind of got this great ability to publish to one and then subscribe to many. And you can have multiple publishers on one topic, multiple subscribers on one topic. It's kind of a many-to-many system. Kind of a standard IoT architecture. You set up an MQTT broker in the cloud, your devices publish to it, and then either devices or services, other systems subscribe to it. So think about like a water system. We would have a soil moisture sensors publishing, watering system listening, and then maybe some cloud-based services listening as well. Now, it's called message queuing telemetry transport. Who thinks message queuing telemetry transport is a message queue? Okay, it's 1, 2, 3, 4 people who are wrong. Yes, it is not a message queue. If this was an episode of QI, we'd get one of those klaxons going, if anyone ever watches QI. No, it's not a message queue. The reason it was named that is because product marketing. It is part of the IBM MQ suite of things. So when it was first invented by IBM, they wanted to package it up with IBM MQ, so they put it with it, even though it's not actually message queuing. You can kind of make it like a message queue, and but it's not really. It is a pub/sub broker. But yes, at least it's close enough. If this was made by AWS, they'd probably call it something like artichoke, and we'll have no idea what it is. But at least we've got a rough idea kind of what it does. Now, who's a Microsoft person, an Azure person? Okay, who's AWS? GCP? Who doesn't care? Okay, most of you. So I'm using Azure services. I used to work for Microsoft, so I know them best. But obviously, all the stuff I talk about is kind of relevant to different platforms. I am going to demo with Azure just because I know that one best. But at the moment, the Azure IoT services are a bit of a mess. Okay, so if you ever look into the Azure IoT services, yeah, it's questionable. So they have a thing called Azure IoT Hub, which doesn't really use MQTT, but can kind of sort of fake it. You're supposed to use their SDKs, and it can do device provisioning, device management, and send and receive data. But although they support it, it's kind of fallen a little bit out of favor with Microsoft. But it was literally just this underlying brokerage. You send data to, data comes off, and then device management. Then they added IoT Central, which had that device management stuff, but a lovely UI. You can kind of drag and drop charts. I want a graph of my CO2 measurement. Drag that in. I want a map where my truck is. Drag it in. Very, very cool. Love it to bits. And I think the current description of it is it's feature complete, which means they can't get rid of it because they've got customers using it, but they're not going to do any more work on it. So, can we use that? I'm not sure. Then they thought, let's go back to square one. Let's build the ultimate IoT platform for our big enterprise customers. And they dropped this thing called Azure IoT Operations. Big, powerful, it's got Kubernetes, it's got Azure Arc, it's got an MQTT broker, finally, yes. All these things, it's absolutely fantastic if you have a factory, if you have millions and millions of dollars. If you just want to use the $200 of free credit that you've got, then you don't want to be touching that, because as soon as you spin up a Kubernetes cluster, you've burned your $200 of free credit in the first 3 minutes. So it is a fantastic tool, but it is kind of way outside the scale of everything we want to do. And what's really fundamentally missing is that beginner thing, that bit in between where I want to prototype something, how can I get started? And that's something that is lacking. So actually, the trick is to go a little bit off book and use Azure Event Grid. It's not an IoT service as such, but it does have an MQTT broker built in, which is kind of very cool. So it's sort of IoT-ish, but not really IoT-ish, but has what IoT needs. But it's a great place to start. It's a great place to start with prototyping, because you spin up an Azure Event Grid, you start sending some data to and from this, and then if you think, yep, my prototype is fantastic, the company wants to pay me billions of dollars to install CO2 monitoring in a skyscraper, thank you very much, then you can upgrade to Azure IoT Operations. Azure IoT Operations uses MQTT. You're already talking to MQTT through Event Grid, so it's not going to be a huge problem you migrating over. So Azure Event Grid, I wouldn't say it's free. For MQTT, it's like first million messages a month are free, and then you kind of pay, it's like $1 per million messages. but they do make you kind of pay just to have it turned on, and it works out about $1 a day to have it turned on. Sorry for speaking dollars. I've been living in the US for the past 5.5 years, and kind of got into that mindset. So, yeah, but maybe 60p to run it for a day, which is not too bad. And obviously, being an Azure service, like any of these cloud services, it has all the security, permissioning, control built in. Yeah, we all know that the S in IoT stands for security. Yeah, but Event Grid has a lot of that. So the MQTT broker, MQTT does support a number of security mechanisms. The MQTT broker does things like X509 certificates, username and password, stuff like that. And all that's supported by Event Grid. And then if you want to connect on the back end of Event Grid, you've got all the Entra and RBAC and all those other names that Microsoft keep changing for managing all the security. And obviously, again, being a cloud service, you've got that instant scalability. Spin up a cheap one for my prototype. Oh, look, install it as Skyscraper, drag the lever, make it more powerful. So it's pretty cool. So let's actually have a look at my Azure Event Grid. Now, what I've created here is what's called an Event Grid namespace, because Microsoft is pretty terrible at naming. I have no idea why it's an Event Grid namespace, but that's what they call it. Again, if this was AWS, it would be called Hippopotamus or something. So at least it's a reasonable name. But it's an Event Grid namespace. And then when I create one of these, in my configuration, to turn on MQTT is literally a tick box. You turn it on, and it's on. Nice and easy. Suddenly I've got an MQTT broker. And that MQTT broker, it provides me, here you go, here's the host name for it in here. So any MQTT can connect to that. Now, as mentioned, MQTT deals with topics, /environment /CO2, things like that. And the way they all work is a little bit confusing. So this Event Grid stuff is designed to be very powerful, and obviously with great power comes really confusing ways to configure stuff. So the first thing you have to configure is what they call topic spaces. So rather than saying, this is the topic I have for my MQTT thing, you define a topic space that contains one or more topics defined by name or wildcard. So you might have a topic space for environment data that contains any topic that's /environment/ anything. You might have a topic for, I don't know, brain's gone blank. You might have a topic for vibration data because you're worried about the lifts. That would be topic space called vibration, and then you'd have /vibration /lift1 /vibration, so on, so on, so on. Now, it seems a bit annoying. You have to kind of configure these topic spaces with multiple topics, but it's done for permissioning. It's done so you can allocate permissioning on a topic space basis. Now, that kind of ties in a little bit with the way they do clients as well. So you have to define which clients can connect to your MQTT broker. I've just got a couple set up here. But you define clients, and then you can define the security of those clients. So a classic example would be I've got 1,000 different clients, all different CO2 sensors, and they're all authenticated with the same certificate. I can do things like that. So I can define all these clients, and that's part of my permissioning. And that way, only my permitted clients can connect using my security mechanism of choice. You know, we don't want a rogue hacker hacking in and saying all my CO2 levels are really, really low, and then everyone passes out in the building. And so you've got that security, and you have these clients, and then you define client groups. So you can actually group clients based off values associated with the client, such as its name or any other kind of attributes you apply to it. So you always get all out the box, which is all the clients. But for example, if you had CO2 sensors and then warning lights to say your CO2 levels are too high, you could have a client group of CO2 sensors and then a client group of warning lights. And then the reason you have these client groups and these topic spaces is so you can set up what's called permission bindings. It all kind of makes sense when we start to think about permission. So what you can say is, I have a topic space for all my environmental data. I have a client group of environmental sensors. These environmental sensors are only allowed to publish data to my environment topic space. They cannot subscribe to data. They cannot publish to anything else, just this one topic space. And so it allows you to kind of build up this kind of mapping of devices to topics to permissions, whether it's publish and subscribe. Yeah. My CO2 warning lights can only subscribe to the environment data. They cannot publish data, things like that. So it kind of gives you a really good level of control, but it's kind of a little bit annoying when you first have to set it up because you've got to configure all these things. It takes a few steps. The documentation is very thorough, but also very confusing. And so we'll see what we've got coming in here. I go and look at my MQTT broker over the past hour. You'll see here's a chart of data coming in. This is all based off the quantity of data. So that's like 12 kilobytes of data when I first connect, and then all my messages coming through. So, just to summarize those steps again, because it is confusing. If you ever work with Azure, everything's based off resource groups. An Azure resource group is a logical grouping of resources in the cloud designed so you can manage that logical grouping as a whole. So if you want to spin up an event grid and a database and a web server and what have you, you put it in one resource group, and then when you're finished with it, you delete the resource group and everything goes away. You don't have these kind of rogue S3 buckets all over the place. You group things by resource groups, and that allows you to control a load of services together. You create your event grid namespace, and then check that box for MQTT. You think about the topics you want to publish and subscribe on, create a topic space for those topics, create all the clients, and if you want to authenticate with like X509, create certificates for those clients, create permission bindings for those client groups to the topics, and then do that for publish and do that for subscribe. So kind of a lot of steps you have to do to get to this point. But once you've done it, you've got an MQTT broker working and running. Now this is a lot of work. There are plenty of MQTT brokers out there that aren't this hard, kind of much easier to use. But if you're thinking, I want to build something that I'm then going to scale into a production deployment, then having one deployed to a cloud provider is probably ideal. If you just want to do a hobby project, Arduino IO, Adafruit, or they all have all these different MQTT brokers you send data to, it gives you a chart, great for a hobbyist, but if you're thinking about a professional deployment, you're thinking about how you take this to the enterprise, something like Azure Event Grid or equivalent services on cloud platform of choice allow you to start and then scale and then support. So yeah, let's talk about connecting from our device. We're using .NET, and there is MQTT.NET. This is a .NET library for doing MQTT. Nice and easy, available as a NuGet package. So if I just go back to my code briefly, I have got, let's just hide this down here, got a little bit of code to create an MQTT connection. And really, it's not that much code. Most of this code is dealing with permissions. So I've got some certificates on my Raspberry Pi. I have an X509 certificate. I load that up. I say I want to use TLS 1.3, whatever. I connect, host name of my event grid, the port, give my client an ID. Every individual client has a separate ID with my TLS options, and then build that. It's kind of following that ASP.NET idea of a builder pattern. And then create my client, connect. A few lines of code, and my MQTT device is connected. And then once I'm connected, really sending data is a one-line thing. So there you go. I'm connected. I get my data out of my CO2 sensor. I stick it in some JSON, convert to a string, and I post that to my topic. One line of code to post my data. And that's what we saw on that chart. We saw that data. That's it coming through. Now, on the other side of the fence, if I want to listen to that data, it's basically exactly the same code. I connect the same way. The difference is I call subscribe and give it a topic. And then that, every time a message comes in, it fires an event. I get the application message in there. I pull that payload out as a string, because you can send strings or binary data. Pull it out as a string, and then I do stuff with it. So it's not actually that much code to do with MQTT. MQTT is designed to be this small, lightweight protocol, designed to be as easy as possible and have minimal impact on your network. It's very, very cool stuff. Okay. So what do we do with this data? Yeah, we're gathering all this CO2 data. What do we do with this data? Well, because we're publishing to an MQTT broker, anything can subscribe on the other end. And then really it's kind of up to you. What do you want to do with the data that comes out the other side? And as I said, multiple subscribers can pull data off an MQTT broker. And so if I was, say, managing a building, and I had lots of meeting rooms in my building, I would probably want some kind of alert system in a meeting room to say, your CO2 levels are too high, get out the room. So that could be just a light on the wall. Light goes red, let's wrap up this meeting because we're about to do dumb things. We leave, go get some fresh air. But also, I'm going to want to look at the trends of CO2 in the building over time. And so I can then gather that data, store that data historically, and then do analytics on that data. So I could see, well, look, these 3 meeting rooms, the CO2 levels are always getting high. Why is that? Are they the most popular meeting rooms? Are we putting too many people in the meeting rooms? What can we do? And you can go, actually, well, you know what? These ones are high, these ones are low. Just an email to the entire company, hey, can you not use these meeting rooms so much? Or we could enforce blocks. Yeah, we're going to close this meeting room for half an hour every hour to improve ventilation. Or we improve ventilation. Actually work on the HVAC system. Maybe there's a fault in the HVAC system in this section of the building, and we can fix that because we have the data. Maybe it's just there's too many people. Easy to solve it, go into the room, take half the chairs out. Oh, not enough chairs in that room, I'm going to go to a different one. So there's lots of ways we can either social engineer, hardware engineer people to not use rooms that have too high CO2. Because as an organization, do I want my managers making dumb decisions? Do I want my teams making dumb decisions? Do I want my CEO making dumb decisions? No. If they're making dumb decisions because of the CO2 levels, it's an easy fix. Now, actually, there was, thanks to Cliff for letting me know about this, there was a device released by Logitech, the Logitech Spot. It's about a week ago or something?
Last week.
Yeah, last week. And this is literally a device that does this. You stick it on the wall in your meeting room. It's got an occupancy sensor to measure how many people are in the room, and it's got a CO2 sensor. And so you've got this data coming out of it. First of all, the light goes off to say get out, but then you can hook into their whole management platform, use whatever APIs they've got, and get things like, okay, well, this room, the CO2 levels are going through the roof, but it's got 20 people in it. We know the number of people. So how do we cut down that number of people? How do we encourage other rooms to be used? And so you've got great sense of stage. And that kind of just built into this Logitech device. So Logitech Spot, it's called. And that's literally their version of what I've got here. Less Raspberry Pi, so less cool. Yeah, there's so much stuff you can do with that data because you've got that ability to send it in and pull anything out. In fact, do a quick demo. I've got some monitor code running, and this code actually measures the level of CO2 that comes out and sets a set of lights. These lights here, Pimoroni blinked. Pimoroni are a UK-based IoT device manufacturer, make great hobbyist devices, very, very cool. This just sits on all the GPIO pins, 8 LEDs. It's supported in .NET IoT, but they haven't actually released the support for it. So the code is written, the code has been merged in to the .NET IoT library, but they haven't actually done a NuGet release since the code was put in there. I was hoping to use a NuGet package, they haven't. I actually wrote the library for this, which is why I'm boasting about it, but it hasn't actually been published yet. But this is connected to the output of my MQTT broker. Yes, overkill, I could just do it on one device, but I couldn't be asked to bring 2 Raspberry Pis to kind of show the 2 separate devices. So if I breathe on this, oh, there we go. It's gone yellow. Yellow is not very good. Green is good. We love green. Green is good. Goes yellow. Oh, hit 1,000. We're going to go up. Red. There we go. So as we're breathing out, if we were in a room that didn't have good ventilation, this would be sitting there, a kind of yellow or red. I actually saw this at home. When I was trying this out, I've got a home office that I work from, and I have a 12-year-old who's obsessed with cats, absolutely obsessed with cats. And don't judge me, I'm not a cat person. Especially when one of the cats likes to walk into my office, up to the side of my chair, and stick his claws in my leg. Do not like that cat. And so I like to keep my office door shut. And so I've got my office door shut, and I'm coding away, and I see my Raspberry Pi is going green to yellow to red. So, okay, I wonder why I'm feeling sleepy here. I wonder why I need a nap. It's gone red. So I open my office door, goes back to yellow, and the bloody cat appears, doesn't it? But anyway, yeah, great for seeing how good those CO2 levels are. And it's literally a monitor process. So my sensor process is publishing to the MQTT broker. My monitor process is just listening. There you can see it says received message. Just scroll down to the bottom. Yeah, received message CO2 1234, 1234, 1170, 1170. So I've kind of built this capability in to monitor these levels and then just put that on a light. Very cool. Okay, so this is kind of, as we think about Azure Event Grid, just kind of the geeky Azure side of things, this is kind of the diagram that Microsoft publishes, because you think about this in terms of part of a whole big ecosystem. So we've really just talked about the apps and devices side. So my device, well, my two devices is my sensor and my lights, that's devices, but I could also have apps that list on MQTT, gather data for making those decisions about what to do. But being an Azure service, as I said, it can connect to everything. You can send messages over HTTP to the event grid if you don't want to use MQTT, and then you build all your services on the other side. You can do webhooks. You know, every time I get a CO2 sensor measurement, call a webhook, things like that. You kind of build it out into whatever ecosystem that you want. So again, very powerful because it is designed to work with everything else in the cloud. I was hoping to do a demo where I send all the data to Microsoft Fabric and show it off in Power Platform with charts and graphs, but Fabric has this annoying quirk that if you create a brand new Azure account, you can't sign up for a free Fabric trial to stop you swamping the system. I don't know. Quick side note, this was free trial-driven conference talk, so I didn't actually start preparing this until 29 days before this, because Microsoft gives you a 30-day free trial. So I didn't want to have to spend any of my own money on actually covering this. So I didn't have time to wait long enough to spin up Fabric to get everything working because of their silly delays. But yes, you can feed this in things like Microsoft Fabric. It's kind of quite easy to create a connector. It's Event Grid goes to Event Hub, goes to Fabric, and then you can plot charts and graphs. And if you've got managers who want to know why you've got a CO2 sensor, you can drag things onto a chart and show them, look, pretty pictures. Managers like that kind of stuff. Oh, and as a top tip, if you want a manager to make what they might think is a dumb decision, get him in a small room, let the CO2 levels rise, then ask things like a raise, because that might be the time you're going to get it. So, what have we learned today? What have we learned today? We have learned that CO2 is generally bad unless you're a plant. Actually, some greenhouses, some industrial greenhouses pump high levels of CO2 into the greenhouse to increase growing yields, because plants eat CO2. But for all of us, CO2 is bad, it is burning our planet, it is making us make dumb decisions in meetings. And you can monitor it with low-cost hardware. What I got here is very expensive for monitoring CO2. That's a $75 Raspberry Pi, add on the SSD. You don't need that. You can do it with a $20 sensor, if that. You can do it with a $5 microcontroller to do it. You can even buy off-the-shelf CO2 monitors. They're about, in the US, they go for about $40. Probably be about £40 here. Usually with a screen, gives you the number. If you're a teacher or you know a teacher, stick one in the classroom. If the number goes too high, get the kids out to recess. And then technologies like MQTT. These are designed for IoT devices to send data. So when you think, how do I connect my thing to the internet? MQTT. There's no point in mucking about with all the other things. It's well established. Everyone knows it. Use MQTT. And then things like Azure Event Grid act as the broker. So think about where you want the data to go to, where you want the broker to be, how you want to scale this in the future, how you want to manage it. And then because you're using an MQTT broker, it's very easy to expand this because you can add more topics that you send data to, you can add more services that subscribe to the data. It's very, very scalable. It's not just a point-to-point connection. It's not like my device is calling a web service, and to do anything else, I have to add another web service. Nope. You want to add a new topic, just publish to a new topic. Nice and easy to do. And going for a walk is good. We are very lucky in this building. The ventilation is pretty good. Didn't really drop below, it's 400 and something to start with. Now we're 500 and something with me talking near the device, people in the room. But the ventilation here is pretty good. But in general, going for a walk is a very, very good thing. Who as a developer has been struggling with a problem, get up and go for a walk, and then you solve the problem on the walk. Happens all the time. Part of that is the fresh air. Part of it's a change of scenery, part of it's the fresh air. CO2 is bad. Now, if you want to build this yourself, if you want to scan this, this is a GitHub repo. This has got all the instructions for building this device. I've got all the code and all the instructions for configuring Azure Event Grid. So if you want to recreate this, you can do it. So Microsoft gives you 30 days free trial, $200 of credit to burn up in that time. So you can do it for free. And then after those 30 days, it's about $1 a day to run Azure Event Grid. And with that, thank you very much. I'm Jim Bennett. I'm head of developer advocacy at a company called Pieces for Developers. You may have heard Scott Hounsman give us a great shout out at the end of his session yesterday. But I'm all over the internet, Jim Bob Bennett. Scan that if you want to get in touch with me. If you've got any questions about what we've done today, please reach out. LinkedIn or Blue Sky for preference. I'm not on the Nazi platform, so please get in touch. With that, thank you very much indeed.